Good morning and good afternoon from your friends at Kubex. I'm Chuck Tatham. I'm CMO at Kubex, and with me is Andrew Hillier, our CTO and co-founder. And we're here talking to you today on the topic of automated resource management for Kubernetes, which is an ever increasing topic of interest. Specifically, we're talking about how we can help and different strategies can help make technologies and capabilities within Kubernetes like HPA, VPA, components like Karpenter, just operate better together to get you better outcomes. And better outcomes is less manual effort, more optimal infrastructure, lower cost, more stable, these kinds of things, which are all things everyone wants. And without further ado, over to you, Andrew.
Thanks, Chuck, and thanks everyone for joining. Yeah, I'll dive right in. And I think this whole slide is a bit misleading because I think we're actually going to make this topic very exciting through what I'm going to show you. So the topic is very sound. This kind of stuff should just take care of itself and not create drama and just work. And that's what we focus on. We are resource optimization. It's AI driven, and I'll show this as we go. We have some really cool agentic capabilities that solve the exact problems we're discussing today. We target Kubernetes, AI workloads running on Kubernetes, and general cloud infrastructure, which is often where the Kubernetes and the GPUs are running. So the idea is we hit the full stack. As Chuck mentioned, we make it much more cost effective, much more performant, fewer operational risks, and do all the work for you so you're not constantly trying to manually change thousands of containers. Let's dig in. There's three key components of our product that are all very important. So at the root of it, and I'll talk about in a second how this works, at the core of it is an ML-driven automation engine. What we're able to do is understand all the workloads and figure out what to do with them and just do it. And I'll show that in several different ways as I go through the demo. Underpinning that is a very powerful and patent pending matching engine that can match to the right node types or GPUs or CPUs or XPUs. So in addition to optimizing all the Kubernetes components, at the Kubernetes layers, we also optimize the infrastructure in a very clever way. And all of this interfaces with our agentic framework. And we're very careful here. We do automation based on deterministic models, so it's very safe to automate. But then there's an agentic layer on top that lets you do all kinds of powerful things. And I'll demonstrate a few of those today. We could probably do a webinar just on that topic. And the key point we're finding is that we have a user interface, of course, that lets you see all this stuff. But we're finding more and more our customers are just interfacing their agents to our agents or to our MCP layer. So instead of a user sitting at a console, which is what we'll be doing today, your AI frameworks can just talk to our AI framework and enlighten itself with all our results, all our data, all our analytics, and access the automation through agentic means. So it's a very powerful way. We see that as the future of using the software would be let your agents talk to our agents. Those are the key pieces. If we kind of go into that ML layer in a little more detail, what it does is it gets a whole lot of data from all the various components that we're pointing at, of course, the containers, the nodes, the cloud layer as well. And we start by doing machine learning to understand the patterns of activity in those workloads. So for a container, or I'll talk about replica set or VPA, HPA, all these things, we can see what's happening at the container level from a resource perspective and also the replication patterns. And we do this at the node layer as well. So at the containers and the nodes, we understand exactly what's going on. And we take that and we analyze it based on policy. So it's a deterministic analysis to determine what exactly we should do to optimize those components. And it gives some very interesting outputs, which I'll show you these. Give you some visualizations of how bad your environment is or how over or undersized or at risk you are at both at the container layer and at the infrastructure layer. But the real goal is to automate, is to just basically flip the switch and say, just make it better. And we've done a ton of work on our automation controller. We think it's the best in the industry, the safest to go and right size the containers either through mutation or in place resizing. And I'm not going to talk a lot about that today because it's a whole topic unto itself, but the automation is key. So you basically get the right answers that you can action, and then you action them and you automate them. And that's where the magic happens. And then all of that, like I said, interfaces with our agentic framework, which kind of overlay on all of it, which does some really cool things, which I'll get to in a minute. The business impact is, from a kind of gratifying PowerPoint slide perspective, is that this on the left is typically what we see in a cluster or a node group where the requests, that orange line, are quite high relative to utilization, which is the blue and gray. So that's the sustained and peak utilization. And what we see is a lot of times in Kubernetes environments, there are excess requests. People ask for a lot. They ask for 2 CPUs, but they're not even using half a CPU. HPA makes this even worse. I'll talk about that in a second. And so usually we see a lot of over allocation of resources that causes you to have to run too many nodes. And that's where things like Karpenter come in, because Karpenter, if you're asking for a lot of CPU and a lot of memory, well, Karpenter has to run enough nodes to give you that CPU and memory. It's just forced to do so. So a lot of times you can't optimize things like Karpenter until you optimize this. And so what you do is if you flip on automation, the automation controller will automatically adjust the requests and limits to be more in line with the actual needs of the workload. And that typically saves a ton. It also gets rid of out of memory kills. It gets rid of throttling. It does all kinds of wonderful things. The environment's clean. You're getting good inputs to the Kubernetes scheduler. We feel that the built-in Kubernetes components work quite well. The scheduler works quite well. The various autoscalers work quite well, but not if you give them garbage in. But if you're giving them good inputs, then they can even do things like bin packing. They do all kinds of powerful things, but it all starts with fixing this up. So that's one of the core use cases. It is vertical scaling of the pods that then allows us to move on to the more advanced use cases to fully optimize the nodes and all the rest of the environment. So that's in a nutshell what we do. I'll talk for a few minutes about the topics of the day, VPA, HPA, and Karpenter. And the idea is that we just want these things to work properly and do their job with no drama and no stress. And like I said, but if you're giving garbage in, then they don't work very well. And it's tricky to make them work. They work well, but they don't work as well. Now, VPA is a different case because VPA is often the source of inputs to the other ones, and it can also conflict with things like HPA. So let's start with VPA and talk about that. Here's an example of VPA in action. And we see customers trying it out. We don't see a lot of widespread. I don't want to criticize it too much because I think it's suitable for some workloads, but it's not suitable for everything because it's a bit too dynamic from what we see. So you see what it's doing here is it's adjusting the requests and limits up and down based on the loads. But in the process, it's creating issues. And so let's just talk about what it does. It's got a few limitations. It basically only allows you to make a fixed ratio of limit to request. So to properly adjust the request, you're adjusting the limit too. And it means that the limit gets in the way quite a bit. You can see it coming down and going back up. And that's usually not desirable, especially because limits, bringing them down doesn't save you any money. And so you're really just artificially constraining the workload. So it's got a fixed ratio. It only looks at, I think, about a week of data. So it doesn't look at longer term trends and say, yeah, that thing lights up once in a while. I really don't want to have it downsized when that happens. So again, it causes it to make things too small, bring things down too fast. It's good for going up. It's not good for going down. I like to joke, it's kind of a bit of an out of memory kill generator from what we see. And you can see it on this chart that every time this workload goes down and comes back up, the out of memory kills. That's one of the flaws in this model is that it's bringing the limit down and it's doing it on short-term data. And so, from a VPA perspective, we see it in use. If you're using our automation controller, it detects VPA in use and won't conflict with it. We'll just let it do its thing. We feel that our scaling is superior. The policies are much more advanced. The analytics is much more advanced. The automation is much more advanced. And like I mentioned, our automation controller will make sure that there's no conflict with HPA, but VPA does conflict with HPA. So we look at limit ranges and reservations or the largest node size, that type of thing, quotas, all that stuff. We find that this is a bit too basic for production use cases in a lot of cases. VPA, special case, and if you're using it, it can frustrate HPA because of what it's doing. Let's move on. And again, in this case, what we would say here is that get that limit up out of the way. There's no reason you should be hitting the limit here. For CPU, you don't even really want to set limits necessarily. There are better ways of doing this by applying a more sophisticated algorithm. Now, there are other ways. If you want to scale up and down dynamically, there are other ways to do it. So this is where our agentic framework comes in. So we actually have an agent, I can show this live, called the predictive pod scaler. And so if I see a workload that looks like this, where you can see it has a time of day pattern. The blue is kind of the sustained activity where it looks like it's quiet as a 24-hour model. So, up to 8 a.m., it looks pretty quiet, and then it goes up for the daytime and it comes back down. And the static recommendation would be to set the request above that sustained activity. So you're requesting enough capacity that you don't cause it to have a shortfall when it runs, and get the limit, the purple line, up out of the way. The request as an optimal setting, the limit, get it up higher. But if you ask our agent to do this, it looks at longer term data and gives a much more stable pattern. So I can say, give me a predictive scaling plan for this thing. And it will say, okay, well, from midnight to 8 a.m. and 6 p.m. to midnight, give it 231 millicores. During peak, give it 1200 millicores. And that looks like this. So if you want to dynamically scale, there are better ways to do it, especially if there's cyclicality in the workloads. It could be hour of day, it could be day of week, day of month. But this is a lot better because it's less volatile. You know what's going to happen, and it comes up before the load occurs, not after the load occurs, so you don't get out of memory kills. This is an example of there's various ways to optimize, but if you really want to be dynamic about the sizing, then you can be smart about it. And in our case, we have agents that will do that and generate these recommendations. Our agents can be human in the loop, or they can be just automated if they're fully deterministic. So it depends on the algorithms in use. This one is actually fully automatable to make this happen. So VPA versus predictive. Now HPA, HPA is very powerful, and of course we don't replace HPA, we work with it, but we make it work better. And one of the challenges we see is it's potentially very wasteful. Now this is a detailed screen here. This is our product, and I just want to make it a PowerPoint version so I can annotate it. What we're looking at here is two charts for a container. It's a deployment running on HPA, where at the bottom we see it's varying from 20 to 40 copies of the container, averaging 30. I'll pull this one up live as well and show it. And the CPU utilization is a top curve. We see it's varying between 0 and around 1 CPU most of the time, peaking above 2 CPUs. So the way you read this is the blue is the sustained activity, the thin gray bars are the peaks and the minimums. And so you can see what this thing's doing over time. It's generally mostly staying below 1 CPU, except for midday. It goes up to maybe 1.5 CPUs sustained, almost 3 peak. So that's a pretty typical workload, and it looks like it's operating fine, but the problem is the request is 4,000 millicores, and this thing's replicated 30 times. So this thing's wasting a lot of CPUs. I'll pull it up live. I think this one's wasting about 70 CPUs in this one workload. We've seen cases in customers where one highly replicated HPA-based container wastes about $250,000 a year in excess infrastructure costs, because that orange line being way up there means that the node autoscaler needs to keep a lot of capacity on the floor to run 30 of these things, even though they're not even using half that capacity most of the time. And you see our recommendation, the dotted line, is to bring that request down to avoid that waste. So this is a good example. HPA is probably working really well. It's just costing quite a bit with this configuration. So vertically scaling that down would make a lot of sense, but also making sure you don't mess up HPA, because if HPA is scaling on CPU, cutting the request in half will cause it possibly to run twice as many replicas. So in the process, you need to adjust the thresholds as well to make sure you do this safely. Otherwise, you'll see some unbounded scaling in HPA. To that end, again, I mentioned there's a lot of waste here. Let me talk about another agent, an HPA optimizer. In that case, I just showed a story of waste. Here's another example where here's an HPA system where a container where it's scaling up to 10 at that point in time. You see the lower curve, it's kind of going up, but it's hitting its max scaling at 10. And when it does that, you'll see in the top curve, the CPU starts going above request and eventually hits its limit. This is a bit of an unhealthy setup. You should either increase the max or do something or change the allocations of it, because when it saturates, when it hits its max scaling, the containers just keep getting more busy. They keep getting more load, but there's not running any more containers to handle the load, and they end up hitting their limit. And we've seen throttling, we've seen out of memory kills, things like that occur. So between this and that waste scenario, what we want to do is kind of catch that. So here's an output of a HPA optimizer agent saying, tell me if there's anything to optimize. You see a little note there. This is not the same example as the left. And again, that's not in the demo system where the right was created, just for full disclosure. But are my min and max setup properties? Is the threshold okay? Am I wasting? Like this lower curve on the left, you see it's sitting at a floor all the time of 4 replicas, even though nothing's happening. And that might be good for performance, and that's the reason it's done. But it also means that you are wasting money all the time on that. So tuning those things very carefully makes a lot of sense. So HPA, again, works great if you give it good inputs, and if the containers are sized properly, and if you configure it properly. And again, this is one we see a lot of interest in, because there's a lot of subtlety in tuning HPA to make sure it works well. So we can automate the requests and limits, but we can also recommend HPA parameters that will make it work better. That was VPA, HPA. Let's talk about Karpenter. And we love Karpenter too. Karpenter is a great technology, again, if you give it good inputs. Here's an example of Kubex automating a recommendation to bring down a CPU request. So that blue line is the utilization of the CPU. It's sitting around, looks like about 100 millicores, but the request is 1,000 millicores. And so if you flip the switch on the automation controller, it'll turn on and say, okay, I'm going to bring down that request to the recommendation, which in this case is 130. Based on the longer term history, you see that workload is at about 130. So we're going to request the right amount, which will optimize the capacity. And in this case, that recommendation was taken. This is an actual live scenario at 2 p.m. on the day it was done. And you see that line come down, and now it's right sized. And it can do that through, we have a mutation controller, but we also do in-place resizing. There's various strategies. You can make them work together even to achieve that optimization. Now, the beauty of Karpenter is that it has built-in auto consolidation. So these are the nodes that were running in the Karpenter node pool at the time the change was made. And within an hour, it automatically consolidated the nodes. And different technologies, the OpenShift node autoscaler will do this as well. It has consolidation thresholds. If you set them right, then it will bring down the number of nodes. So this is a case where by automating the sizing of the container, Karpenter just automatically goes and optimizes the nodes and saves a ton of money. And so that's from the Amazon console. That's the node cost curve for that environment. Karpenter's great, but again, if everything's oversized, Karpenter's hands are tied. It has to run more nodes or the wrong kinds of nodes. We see a lot of times you're running CPU optimized or general purpose nodes when it could be running memory optimized nodes. And it all comes down to optimizing the resources so it can do its job properly. Last slide, and then I'll pull everything up live and walk through some of this stuff. There's also another agent. It's pre-released right now, but it is a Karpenter optimizer, and you can do things like give me a node pool spec for a cluster. And it will say, okay, based on all the activity and what's optimal and what the optimized settings are, it will go and give you the node pool spec, the optimal spec, saying here's the types of things you should run, here's the sizes that you should be leveraging from. So just giving it marching orders so it can go off, and when it does what it does, it's choosing from the right set of things from a more enlightened view. So this one also is very interesting. You can do similar things for machine specs in OpenShift and things like that. This is a very powerful way to say, okay, Karpenter, do your job, but I'm going to give you a little better inputs so you can do it more efficiently and more effectively. And so, again, we like Karpenter. It's a great way to actually realize the savings and to drive elasticity even better if you configure it properly. What you're looking at is the front end of our user interface. Like I said, there's a rich user interface. You can use all you want. With automation enabled, you don't really need to use the user interface unless you want to go in and look at some things. It just does it all automatically. And like I said, agents are being more and more a way into this. And you see our agent on the left-hand side here, and I'll get to that in a minute. So I'm just looking at an overall overview of my Kubernetes environment. And the example shown here, this is very important. I'll take a second to explain this. So this is one of the main things. We're just looking at one cluster right now. I'll expand out in a second. But this is a chart of the gray line is the allocatable resources for CPU and memory deployed in that environment. The orange line is the amount of requested resources within that pool, how much all the containers are asking for, and the blue is what they're using. And so what you end up seeing is a lot of times, especially you see on memory over here, there's quite a gap between what you're using and what you're asking for, and for what you're asking for and what's actually running. And the bottom gap is fixed by vertical scaling, by right sizing the container. So you're not asking for too much. And that will shrink that gap. And when you do that, then the node autoscaler can run less infrastructure. And that comes down, and that's where you save money. And if it doesn't do it automatically, you can do things like bin packing to bring that down to make sure you are running efficiently. And so this is an actual scenario of an environment where automation was turned on right around here, and the requests come down and down for CPU and for memory. And as a result, the amount of running hardware comes down. And so that's what good looks like. That could be individual containers. That could be things scaling with HPA. Like I mentioned, if you right size something running HPA, you usually see a pretty big impact because it's got a multiplier effect. And we brought it down and down. And you can see down here, I won't go through all the areas of this console, but there's the automation dashboard here where I can pop it open and see that happening. So here's a cluster, here's a namespace, and here are a bunch of containers that are being automated, and you can see the impact on them. Let's go to this bottom one, has a nice example where we're automating up the CPU requests by 0.7 of CPU and bringing the memory requests and limits down. We automate in both directions. The left is really risk mitigation. You want to make sure you're asking for enough resources, or again, the scheduler doesn't work very well. The right is cutting the fat and getting rid of the excess so we can save some money. We usually see it going in all directions, but the net is usually savings, most clusters. That's the automation occurring on that environment, and that's realizing that savings. That's one key point. And again, this is being done in a way that if VPA is active, then it will let it do its thing. But if not, this would replace that and do it in a much more intelligent way. If the HPA is running, then it's going to run much more efficiently. And Karpenter might be the way that those nodes are coming down depending on the autoscaler in use. I'm going to zoom out here for a second and just look at all the clusters. There's 18 clusters in this system. They're just a bunch of lab environments and stuff like that. And it's a little more messy when I do that because you see there's some things that are coming on and offline. There's a big ramp where something went online very recently. But I can see by cluster, what my opportunity is and what all my risks are. So there's a lot of savings opportunity by downsizing. And there's also risks. I have nodes that are maybe unhealthy. Maybe they're running 100%. I'm hitting my max pods per node. That's a really important one that can cause a lot of cost in some environments. And I also have containers that are hitting their memory limits or throttling or that type of thing. I'll cover that in a second. But let me just do a little deep dive down in here. I'm going to click on my cost and waste, and I can see for this cluster, there's quite a bit of waste. And here's my node groups that are running. And I can even right here, just within a couple of clicks, see, yeah, the requests are way above utilization, like I showed in PowerPoint. That's what it looks like in practice. We should be able to optimize this environment. This isn't the one that was being automated, and bring that down and run on half as many nodes. We could even run on a different type of node. We can probably run on a memory optimized node if we bring that down far enough. So I can see at the hardware level, at the node group level, how inefficient I'm being. And this is what it typically looks like. Memory's not too bad. CPU is way oversized. So at the cluster, at the node level, we have a lot of inefficiency. And so, but we fix that by fixing the container. So if I click up here, I'll see all the recommendations. I'm going to click on this little graphic, which is going to take me to what we call the histograms. So this is what's causing that problem. This is how badly sized the containers are. And I'm looking at that one cluster, but I'm going to expand out and just look at all my clusters. I can actually look at my entire environment here. Here's all the clusters in my environment. And I won't spend too long on this, but what this is saying is that from a CPU request perspective, some of them are okay. The red are undersized. So a lot of containers are too small or don't have a value, but a ton are way, way too big. And this is what we see everywhere. This big yellow bar means cost. Red and gray are risk. Yellow is cost. So I've got excess cost. I've got way oversized containers. I've got some undersized for memory. I've got some memory limit issues. Things are hitting the memory limits. Lots of problems here. But I can just get here very quickly. I can see what my top recommendations are, and I can fix them. And this is the example I showed in PowerPoint. This is that container that's running 30 replicas, 4 CPUs each, and they only need about 1.5 CPUs each. This is the live version of what I was showing in the PowerPoint. Here, the request is 4 CPUs. We're saying it can be down lower to here. You don't need requests above your peak. I can look at all the historical patterns and say, what is this thing actually doing? I can even go down to the 5-minute data. So we're not intending to replace things like Grafana, but what we want to do is when we give a recommendation, all the evidence is right here at your fingertips. And we're saying this one can be downsized safely. You can automate it, and you will save almost 70 CPUs as a result. And this one is running HPA, and here's the replication pattern of this container, and I can see again what it's doing over time. So this is a case where optimizing that HPA is probably working fine. It's just costing quite a bit of money in this configuration. We can fix that. The other example I'll show quickly is things hitting their limits or for throttling or out of memory kills. I can very quickly see, I'll go to the second row here. Here's a DynamoDB where for memory, it's just hitting its limit. The purple line is the limit. We're recommending getting that limit up out of the way because you're just creating a lot of out of memory kill activity. The idea is we want to fix those risks. We want to optimize the sizing of the workloads to make sure that we're not incurring excessive cost. If you do that, like I said, HPA works better, and Karpenter will then go and automatically consolidate, and you get huge benefit. From here, what I'm going to do is just take a second and talk about the agents that do this. So I'm in the main agent right now, but I can flip into the sub-agents, and I only have some of them loaded here, so I can't show all the things I showed in the PowerPoint, but I'm going to go to the predictive pod scaler agent. I'm just going to grab a prompt from my PowerPoint here, and I'm just asking it. So this works a bit like Lovable, where I type on the left and the right-hand side will change as I go. And what I'm asking it to now is just a simple thing. I'm just asking it to go to a certain container. The agents know how to navigate the UI. They have access to all the raw data, all the analytics, all the automation status. And so I've navigated to a container, which is, again, the one I showed in PowerPoint. You can see it's got a deterministic pattern that it carves out over days. This is the 24-hour, this is the machine learning model. But if I go to down to the hourly level, what that's coming from is most days it goes up and does a spike of activity. With that, the agents can actually use that to say, well, I can do a predictive plan. So generate a predictive scaling plan. And that's going to analyze that data. And this is an hour a day by default scaling plan. But again, if it's got cyclicality at different levels. So here it is in agentic fashion, giving us a whole bunch of information. Basically, in here you see the low off peak is 234, on peak is 1200. I can say be more concise, which I find I do with a lot of AI. And you can put that in your personal prompt to say, just give me tables back and that type of thing. So that's an agent that's analyzing and saying, okay, and we can send that to an automation controller to say, okay, schedule up and down on that schedule. We'll save a bunch because we're not keeping the requests high all day long. So it's less volatile than VPA, but it's very effective at saving money. That's a predictive pod scaler. I can also go out to the main agent and do some other things. Like, let me see here. I'm just going to paste this one in. I didn't talk about AI, but we also have a bunch of AI workloads in this. I have to spell right. It actually handles spelling quite well, but I can say, show me the recommendations for my least efficient LLM running on GPUs. And so this is just another use case just to show the power of this, that the framework is also analyzing all the AI workloads and optimizing the GPU configurations, and it can take you there and show you that. Here's an LLM. You can see up here it's called LLM, and it's running on a GPU, and we're recommending you run on a different GPU that's much more efficient and much less expensive. So it's actually able to do a full analysis of AI workloads against GPUs and against cloud catalogs and recommend how to optimize AI workloads as well. And that's a bit off topic for this webcast, but it just looks super cool. And it is one of the power of the agents. I'll stop here as far as demoing. Hopefully everybody gets the idea that from a VPA, HPA, Karpenter perspective, this is a really great complement to drive efficiency, to automate, to handle some very specific use cases. And again, these agentic use cases, more and more coming. The node pre-warming, for example. Can I bring up the number of nodes running before the loads hit? New container sizing, that's a popular one. I'm about to run another Nginx. How big do I make it? And it looks through all your current ones as well. You should probably make it this big. A very rapid area of advancement for us is on the agentic side to drive more and more functionality, including more advanced ways of optimizing HPA and Karpenter.
It's a great way of making really deep and detailed information accessible in really useful ways to have that way of querying.
Yep, absolutely. And like I said earlier, we're finding customers will just interface their agents into this. And so everything I'm doing in the UI can just be done from your AI frameworks. And that's when it gets really powerful because your agents have access to all of this, all of the rules behind this, everything are available from the agentic frameworks.
A couple of resources, technical resources that you guys might be interested in. One is on Kubernetes resource management, a lot of the themes that we've talked about here in some depth, and that's the top one. And then a new one is an e-guide on optimizing GPUs for platform owners. That's a big area of interest as more and more inference workloads land in Kubernetes. GPUs are managed quite differently than CPUs. They have special requirements, and in order to get optimal efficiency, they need to be treated as such. There's a little bit of technical prerequisite as well as far as getting the right data. So invite you to download either of those. A great way to experience what Andrew was showing today is our free trial. This is truly a free trial for 60 days. If you have an infrastructure you'd like to see through this lens, it's a great way to do it. We do follow up with you and see if you need any help, but really it's a self-guided trial. And so there is one question, Andrew. Question is Kubex application aware? Does it take into account error rates or latencies? We have Datadog, so resiliency is also something we are interested in.
That's a great question. And that's actually where the agentic framework comes in because that is a conduit to do exactly that. So one of the things, the trends we're seeing, and when I mentioned this agentic integration is that we can also hit, or you can also hit, or combine Datadog's MCP layer and start to enrich it with that kind of data. So that can be factored in, absolutely. Basically, there's various ways to do integrations, but now we're finding that the MCP layers are a great way to do exactly that. So they can contextualize things back in. Out of the box, it's not going to do it just when you run a trial, for example, you're not going to see that. But through the agentic frameworks, being able to bring that data over is the path for that. And we're hearing more and more about that, of contextualizing it. The big one for us, for example, is Java JVMs. And so we have special policies for optimizing JVMs. But of course, what you really want to do is get some JMX stats into there. And we actually have a JVM optimization agent that's coming that will do all kinds of more powerful things around right-sizing them, making sure that you're not affecting garbage collector concurrency, things like that. So there are app-specific policies and algorithms, and we're finding more and more that the data plane, the agentic layer is a great way to do that type of integration with observability tools to enrich the answers.
Thanks for that question. Any other questions from anyone as we move to wrap? Again, invite you to try out the trial and or download any of those assets. They are truly technical references, so enjoy them. Andrew, thanks for the time today. Thanks for the great demo. And thank you all for joining. Have a great day.
Thanks, everyone.